In this example, we're asked to show that if x plus y is greater than or equal to 2, then either x is greater than or equal to 1 or y is greater than or equal to 1. So let's write this out. Again, we use some logical symbols here to try to get a feel for what's going on. We'll call this statement P, and we'll call this statement Q, although this is a compound statement. So we're going to look closer at that in a minute. And then we have our implication, P implies Q. All right. We're going to try to prove this by contraposition. So the contrapositive of our statement is, as always, P implies Q is logically equivalent to not Q implies not P. So let's take a closer look at Q, right? So Q here is a disjunction of two statements. So Q is actually a disjunction of x greater than or equal to 1, right? Or y greater than or equal to 1. If we want to take the negation of this, we have to apply a De Morgan's law, right? So not Q is then going to be equal to not x greater than or equal to 1 and not y greater than or equal to 1. And what does this become? Well, these two negations here, we know what that means. If x is not greater than or equal to 1, then x must be less than 1. And then we have our conjunction. That's part of De Morgan's law, right? And again, negation over here is going to be the same, that y must be less than 1. All right, so here's our assumption. We are going to assume the negation of Q, and we are going to try to prove the negation of P. Well, what's not P going to be? Not P is not a compound statement like this. It's got both x and y involved in it, but it's simply stating that the sum of these two is greater than or equal to 2. So not P is just going to say that x plus y should be less than 2. Okay, so let's go ahead and prove this one. This one should be pretty straightforward, I think. It's mostly a matter of choosing to use contraposition. I'm not claiming that this is the only way to prove this, but choosing to use contraposition and then properly writing out the negations and knowing where to start. So let's write our proof. So, as always, start with proof. Now we need to first state that we're using real numbers. So let's let x and y be real numbers such that, and here's where our assumption of not Q comes in, x is less than 1 and y is less than 1. All right, so as always, we want to write out almost all of our proof in words, but we do allow for this symbolic x and y are real numbers to save us some writing. So we let x and y be real numbers such that x is less than 1 and y is less than 1. All right, then what's true? Well, we want to add these up, right? So then x plus y, let's just go one at a time, right? So this is going to be less than 1 plus y. Why is that? That's because x is less than 1, right? Which is in turn going to be less than 1 plus 1 because y is less than 1, but this is of course equal to 2. This is maybe one of the most straightforward, at least math-wise, as far as the math is concerned, right? This is one of the most straightforward proofs that we're going to see in this course. But look what we've shown here, right? Let's just combine it all. Therefore, what? X plus y is less than, strictly less than, so x plus y is strictly less than 2. Now, what's the whole point of this, right? We want to then apply the contraposition to state our conclusion that we were asked to prove, right? So we can say, by contraposition, we have shown that if x plus y is greater than or equal to 2, then the negation of this statement is true, right? But we know exactly what that is because we did the work ahead of time, right? So then x is greater than or equal to 1 or y is greater than or equal to 1. And that's it for this one. This one is nice, fun, very straightforward, easy to unpack example that hopefully shows you the power of proof by contraposition.